Hi, this is Jake Fry, and today I'm going to teach you about coordinate systems. This is the first video in my series that I'm going to make on mechanics. So, in coordinate systems, I'm going to describe how you can successfully map a physical space into a mathematical space, which will help in your future problems. So first, what are coordinate systems? Well, essentially, they're just a method of assigning locations in a manifold of Euclidean space, which is just a fancy way of saying real physical space. So, the location itself depends upon the variables in question in your function. They don't necessarily mean position, even though I did say location. In physics, it's very common for your coordinate system to be a bunch of position locations, but it's not necessarily the case. So in this little cartoon, in one dimension, I have a location for the house, which would be horizontal position equal to 0, versus the school, a horizontal position of 19. And so now we could do things like determine the distance between the points, or if there's a tree in the way at 10, we would know how far away it is from the house or the school as well. Additionally, you can do things other than just position data points. So, for example, in this two-dimensional graph cartoon, we have many different points that create this blue bell shape or normal distribution. And so we've seen this many times in mathematics where you can describe a normal distribution to get the mean, which is this line, or the full width at half max, things like that. And you wouldn't be able to do that without being able to assign each data point to a location in your coordinate system. So what are they used for? So any mathematics problem you can imagine, from physics to economics, biology or sociology, uses coordinate systems in order to visualize the data that you're collecting more easily. So how do you create them? Well, first you have to determine which characteristics of the points you want to plot. So this could be like a geometrical model, so like a sphere or a cone. It could be things like a trajectory of a planet, or even the cost of all the ingredients required to make a pie. So then what you have to do is identify the dependent and the independent variables. And so a lot of times in earlier math courses, we'll learn like x is always the dependent variable and y is always the independent. But as we'll see in physics, that for more than one variable, it can be different. So you have to be careful when identifying the dependent and independent variables. So for example, this function of two variables, so f of x and y, equals the sum of g of x, which is a function of x, plus h of y, which is a function of y, we would see that both x and y are dependent variables in this function, and that f of x and y is the independent variable. So you just have to be careful not to get confused if you're thinking in the way that you used to remember what's the dependent and the independent variable. My circle is a little bit too big. Let's see. Move it up here. Okay. And then remember, the function f doesn't need to be known. So it could just be a mapping of data points. So if you had, you made a measurement and you don't exactly know what trend it's going to take, you can still assign a location in your coordinate system without knowing the full functional form. So just, keep that in mind. Okay. All right, so then each variable must be independent of the other variables. So this makes it so that if you change along the vertical axis, you don't have to mix in a bunch of trigonometry in order to see how much in the horizontal you're affecting. So this is, on almost all of the applications that you'll see, you're going to want to make a coordinate system like this. There are some cases that are skew coordinate systems where one of the axes is tilted and so has a component of a different variable. But that's outside of the scope of this talk. Okay, so in position space, this can be visualized as horizontal position as one variable and vertical position as another variable. And geometrically, when you make each of the variables independent, that means each coordinate direction is perpendicular to all other coordinate directions. However, even though the coordinate directions are perpendicular, this does not mean that the coordinate system must be rectilinear, so by fancy word, rectilinear just means like a grid-like shape. So if you think, like I said before, vertical is y in this direction is the vertical direction, and x in this direction is the horizontal direction. This is a valid coordinate system, but you can create a transformation on this coordinate system, so this transformation f, to kind of stretch and twist the coordinate system. Each of these grid points are not rectilinear anymore, but if you look right at the intersection between each horizontal and vertical plane, they're still perpendicular to one another because each of the variables are independent. Okay, so in a generalized coordinate system, so where q1 is one of the variables and q2 is another, you can have each of them increasing in your coordinate system, but the location where they intersect, they're perpendicular. So E1 and E2 are the unit vectors in this rough example, and they go in the direction of where Q1 is increasing is E1, and where Q2 is increasing is E2. They don't necessarily have magnitude of 1, but this is much later that we're going to have to worry about stretching and twisting coordinate systems. And so how many dimensions are needed when you create a coordinate system, and should you be afraid of higher dimensions, like a little black hole? So first, how many dimensions are needed? So this depends upon how many independent variables you want to describe in your system. And should you be afraid of higher dimensions? No. So with practice, it's as simple to keep track of, say, 15-dimensional coordinates as it is a one-dimensional system. All right, so the first example that we have, most of us already know about, is Cartesian coordinates. So this is a system of coordinates where each point is identified by its location on a set of perpendicularly oriented lines, where the number of lines equals the number of dimensions. And each of the variable dimensions is subdivided into increments separated by integer amounts. So, some examples, because that was a mouthful. So in one dimension, it's typically called just a number line. So you see how it's subdivided in integer amounts. It goes along one axis, because it's in 1D, since the only variable that we're considering in a number line is in the one dimension, and it has an origin. And yeah. And 2D, so this is probably very familiar as well. You have an x along the horizontal and a y along the vertical. To keep us informed with generalized coordinate systems, Q1 would be x and Q2 would be y, and the unit vectors E1 and E2 would just be along x and along y. And in this case, it would be of order 1 magnitude. And so you can easily, from here, just x and y for the position. For the origin is 0, 0. This red point is minus 3x and positive 1y. And positive 2x, positive 3y is green here, and so on. So it's very easy to map out. But when you get to 3D, this is where a lot of people get confused with coordinate systems, even though all you're doing is, instead of having 4 quadrants, you now have 8 octants to deal with. But it's all the same. You still have a position this time Q1, Q2, and Q3 because it's in 3D, where this time Q3 is Z, which is the vertical axis here. In the future, there will be a lot of what is called right-hand rule, and that just means the orientation of where the x-axis is increasing and the y-axis is increasing with respect to the z-axis. And so basically, if you have your hand, your z-axis is your thumb, your x-axis is your index finger, and your y-axis is your middle finger. And so, yeah, right-hand rule is the way to go. And so, yeah, to find a point on this little box, you just go x over in the positive direction, y, and then z. Okay, and then if you have nd, so, n being an integer number of variables, dimensions. So this is much harder to visualize since we only live in a three-dimensional world. Well, more or less, but it's very simple to ascribe a coordinate system. So one that's very common in physics is the fourth dimension, where each variable here, so we have x, y, and z, and we include time as the fourth dimension. We multiply it by the speed of light to give us the same units, since normally this is in position space, so everything would be in meters. So the speed of light times time would give us units of meters. But outside of physics, higher dimensions than 3 are also quite common. So like my pie example, so you would need apples, sugar, brown sugar, pie crust. So that's already 4, and you probably need more things to make pie. I just don't know. But yeah, so it's very common. And also in physics, probably outside of what I'll ever talk about, since I do atomic physics, but there's things like in particle physics, some beyond standard model ideas using supersymmetry, and then a lot of people know about string theory, and there's, I think, 15 dimensions for one of the most common models using string theory, but it's just, keeping track of variables is the way to create your coordinate system. Okay, so we already can describe in space whatever dimension we want the location of a data point. So why exactly would we ever want to use anything other than these rectangular grid shaped pattern Cartesian coordinates? Well, it turns out that some problems are much easier to solve using curvilinear coordinates. And curvilinear just means, unlike rectilinear, it curves. So, for example, this circle, so x squared plus y squared equals 4, so we have a circle of radius 2. It's, easy to say at this point on the x-axis, x equals 2, y equals 0, and similarly at each of the points along the intercepts. But if you want to choose some random point off of one of the intercepts, then you have to use a lot of trigonometry, and whenever you can avoid trigonometry is always the best because it makes solving problems much faster. So the first example is polar coordinates, where instead of x and y, we change our generalized coordinate to r, the radius, and phi, the angle. And so in this case, we can easily see how to convert from horizontal position into r cos phi, and also the vertical is r sin phi. So we can still get back the Cartesian coordinates using this other coordinate system. But in this case, it's much easier to define just, you have a radius of 2 and you have an angle phi, and so you can determine phi goes anywhere from 0 to 2 pi or 0 to 360 degrees, depending if you want to use degrees or radians, and then you can easily track along a circle. So Yeah, polar coordinates are great for that. All right, and then we can extend polar coordinates into a third dimension by using cylindrical coordinates. And so in this case, we call, instead of r, we use rho instead for q1 for a generalized coordinate. And the vertical direction z is used for our third generalized coordinate. And so this type of system is quite useful when you have things that have symmetry about a certain axis. So like if you have a really big metal pipe and you want to know where you are on that metal pipe, if there's some mechanical defect or a hot spot in the pipe, to keep track of what happens to, like, say, the electricity flow through the pipe or water flow if it's a water pipe. This coordinate system would be far easier to use than, say, a 3D Cartesian coordinate system. And then another very commonly used curvilinear coordinate system is spherical coordinates. So in this case, we have the radius. For whatever reason, people typically use r instead of rho for spherical coordinates, but not cylindrical coordinates, but that doesn't really matter. Phi is in physics, so be careful. In physics, phi is the coordinate between the x and the y axis that goes from 0 to 2 pi, like in polar coordinates. And it's theta in mathematics is the convention, but since I'm a physicist, I use this convention. And then theta is the angle away from the vertical axis in this case. And so you would use spherical coordinates for anything that follows an arc along a sphere to describe, charge density inside of a chunk of, I don't know, resistor. I'm not sure. But yeah, to describe anything with a spherical shape or dome-like shape, spherical coordinates are very useful. And since we live on planet Earth, which is more or less a sphere, it's very useful for things in physics to describe things like orbits around the Earth. Okay, so how to choose between these basic coordinate systems? So you should look for symmetry in the system, since if you can find an axis of symmetry and match it with your coordinate system, you'll reduce quite a lot of trigonometry that you would have to use in order to find, like, say, the distance between 2 points or whatever else that you wanted to do. And then also you want to place the origin and the direction of each axis of the coordinate system, once again to minimize required trigonometry to solve the problem. And this will be very clear in the mechanics lessons, intro mechanics, that I'm going to have in future videos. Alright, and so then more advanced treatments of coordinate systems, which I was kind of trying to motivate using generalized coordinates Q1 through Q3, are very important for things like Lagrangian or Hamiltonian mechanics, which we'll be discussing later. But just for like a quick teaser of generalized coordinates. So if you have fixed vertical and horizontal axes, x and y, when could things like generalized coordinates be helpful? So in this case, where you have a triangle and your particle, which is this little orange guy, is traveling along this blue line, you can create a generalized coordinate system such that you could describe the entire motion of this orange particle with theta and with s, the distance along this line, which would make it far, far easier than describing this point along x and y as your coordinates. And this is just as easy as mapping the same two generalized coordinates along a particle that's in an open path, like here, and also in a closed path. And so this will become very important when we get to mechanics problems that are very difficult to solve just using Newtonian mechanics. But yeah, so that's a brief introduction of coordinate systems, and let me know if you have any questions. And yeah, hopefully you'll stick around for more videos, which will be far more interesting, I promise. But a lot of people have problems with coordinate systems when they first start out in physics. And yeah,